There is a wound on the face of the sun right now. Not a flare, not an explosion, not the cinematic fireball you've seen 100 times in stock footage. This is something stranger. A vast, ink-dark gash tearing across the glowing surface, a void big enough to swallow dozens of Earths and still have room to spare. And as you watch this, that wound is slowly, silently rotating into perfect alignment with our planet. If you pull up a live image of the sun, the kind NASA publishes every few minutes, you won't see a dramatic blast. You'll see what looks like a smudge, a dark canyon in the solar atmosphere, no arcs of plasma leaping into space, no obvious violence. The sun looks calm, almost boring. A soft, steady disk of light with a bruise on one side. But from that bruise, from that apparently quiet patch, an invisible river is already pouring out. A torrent of charged particles, mostly electrons and protons, is streaming away from that dark region at hundreds of kilometers per second. Faster than any bullet ever fired on Earth. Faster than anything humanity has ever built. A continuous flow, day and night, unblinking, unbroken. You cannot see it. You cannot feel it. But it is out there, spanning the 150 million kilometers between the sun and us. A highway of plasma connecting that wound to the magnetic skin of our world. In an office in Boulder, Colorado, at NOAA's Space Weather Prediction Center, forecasters are watching those streams. They watch the solar images, they watch the upstream solar wind monitors 1.5 million kilometers from Earth, and they watch their models. And sometime recently, looking at that dark gash turning toward us and at the data already trickling in, they did something they do not do lightly. They issued a geomagnetic storm watch. On paper, it looks simple. G2 possible, conditions unsettled, elevated risk for auroral activity, minor impacts to high-latitude power systems and spacecraft operations. A few tidy lines in a technical bulletin. On the sun, nothing storm-like appears to be happening. If you were expecting a massive solar flare, a blinding flash, a mushroom of plasma erupting into space, you would miss it. There was no flare, there was no obvious blast wave. To anyone glancing at a standard white light image of the solar disk, the star looks like it always does. A glowing ball, a couple of sunspots, not much else. And yet the people whose job is to warn power grid operators, satellite controllers and airlines that space is about to get rough have just raised their hands. A storm warning without a storm. That contradiction is where this story starts. Because if you're used to thinking about space weather as giant explosions that sometimes hit Earth, what's happening right now does not fit the script. There has been no headline-worthy flare, no viral animation of a cartoon sun sneezing plasma at our planet, just a dull black wound rotating across the face of the star and a line in a forecast that only a few thousand specialists ever read. But whether you know it or not, your life runs straight through the things that forecast is about. The map app that snaps your location onto a street in a fraction of a second. It depends on timing signals from satellites flying through that invisible river of particles, the power flowing into your laptop, your router, the servers delivering this video to your screen. It moves across transmission lines that can have electrical currents induced in them when Earth's magnetic field starts to shake. The plane that just flew over your house, the cargo ship threading a narrow approach channel on the other side of the world, the emergency response team coordinating over radio in a storm-hit region. All of them lean on systems that assume the space around our planet is, if not quiet, at least predictable. Right now, that assumption is being tested by something that does not look like a threat at all. The sun. To a casual eye, is fine. The news is busy with other things. There is no countdown clock on the evening weather segment warning you that a high-speed stream of plasma will arrive Tuesday, give or take 12 hours. If you walk outside tonight and look up, the stars will look exactly the same. Your phone will work, your lights will turn on. Civilization does not twitch visibly when NOAA posts a G2 watch. But at the edges of our awareness, a different picture is forming. Engineers are forwarding that bulletin to each other. Operations teams are quietly checking procedures. Do we need to adjust satellite orientations? Should we lower load on these particular transmission lines? Are polar routes still the best choice for these flights over the next 48 hours? No one is panicking. Right, no one is sounding an alarm on TV, but the storm warning is real, and the wound on the sun that drives it is not a one-day event. That is the part that matters. Because this is not a flare that explodes and is over. This is not a single punch that either lands or misses. What's pouring out of that dark region is continuous. It has been flowing. It will keep flowing. The sun rotates roughly once every 27 days as seen from Earth. That means this wound, this coronal anomaly, will turn out of view, spend about 2 weeks on the far side where we cannot see it directly, and then, if it persists, rotate back into alignment again, and again, and again. Every time it does, the same kind of invisible river will sweep past our planet. Every time Earth's magnetic field will flex, its radiation belts will respond, its fleet of satellites will take another dose. Every time the same quiet office in Boulder will have to decide whether to send out another advisory, and every time most of the world will not even know it happened. So the interesting question is not the one that usually gets asked when a solar storm makes the news. It is not, will it hit us? It is hitting us. It has been hitting us in a low-level way for days already. It will keep hitting us as long as that dark region remains open. The question that matters is different. What does a repeating wound on the sun do to a civilization that has wired its nervous system into orbit? What happens when your navigation, your finance, your communication, your weather forecasts, your power grid, your entire digital mirror world depend on machines drifting through a region of space that gets hammered on a 27-day schedule by a force most people have never heard of? How many rotations can that system take before something important, something we all quietly assume will just work, finally doesn't? That is the story this video is about. And the dark patch on the sun you can barely see on a monitor in some forgotten tab of a government website, that is where the story begins. When most people hear the phrase solar storm, they see the same movie in their heads. A blazing knot of magnetism twists itself into a knot, snaps, and unleashes a tremendous flare. An eye-searing flash bright enough to overwhelm spacecraft sensors and saturate camera detectors. A great arc of plasma heaves itself away from the sun's surface, billowing out into space as a bright, ghostly halo in coronagraph images. Animations on the evening news show a fat, glowing bubble racing across the solar system like a slow-motion cannonball aimed at Earth. That picture isn't wrong. Those are coronal mass ejections, CMEs, and they really do drive some of the most dramatic space weather we know. They're cinematic. They look like what danger is supposed to look like, a single violent event, a visible blast with a beginning, a middle, and an end. This time, none of that happened. There was no X-class flare clawing upward on the graphs, no easily shared clip of a bright cloud erupting off the solar limb. If you were watching the usual flare alerts, you saw almost nothing. The last few days' coronagraph movies, the ones that block out the sun's disk so you can see plasma flying away, showed small ejections heading off in random directions, not a big, obvious, Earth-directed shell. And yet, in that office in Boulder, the same office where they watch for those classic big ones, a geomagnetic storm watch was issued. Not a vague, conditions unsettled note. A specific call for a G2 level geomagnetic storm on NOAA's 5-step scale. On paper, G2 is moderate. In practice, it is not trivial. It's the level where power system operators at higher latitudes start checking their geomagnetically induced current monitors more often. Satellite operators consider switching some spacecraft into safer modes or postponing sensitive operations. Airline dispatchers look at polar routes and ask whether they'd rather not be flying through radio-noisy skies during the peak. NOAA does not throw that flag for fun. Their warnings go into operational playbooks. Grid operators in places like Canada and Scandinavia literally have pages that say, if a G2 watch is issued, do X, Y, and Z. Under normal circumstances, there's a familiar sequence to these alerts. A big active region rotates into view. It crackles with flares. One of those flares is accompanied by a CME that leaves the Sun in the general direction of Earth. Spacecraft like SOHO and Stereo catch the eruption in profile. Modelers at NOAA and NASA run propagation codes that estimate when that plasma cloud will arrive and how strong its magnetic field might be. Based on that, forecasters decide whether a G1, G2 or higher level watch is justified. The chain of cause and effect is visible. You can point to a video of the Sun and say, that's the source of the storm watch. This time, if you go hunting for that moment, you come up empty. No obvious flare, no textbook halo CME engulfing the coronagraph's field of view. Just that sprawling, quiet-looking dark region on the Sun, and a forecast saying, expect Earth's magnetic field to get shaken. Yeah, to understand why that's weird, and why the people who watch this for a living sat up a little straighter, you need to understand what exactly a G2 storm means in the first place. The G-scale you see in NOAA bulletins is tied to something more fundamental, an index called KP. KP is a number from 0 to 9 that tells you, in a single digit, how disturbed Earth's magnetic field is on a global scale. It's built from measurements at a ring of geomagnetic observatories around the world. Each station watches how far its local magnetic field wanders from its usual quiet day value. The bigger the wiggles, the higher the local K at that station. KP is essentially the averaged, rounded-off summary of all those stations put together. On a normal day, with the solar wind blowing at a comfortable background pace, EKP sits down near 0 or 1. The magnetosphere is relaxed. The oval where auroras live hugs the polar regions tightly. High-frequency radio signals bounce predictably off the ionosphere. GPS signals pass through the upper atmosphere with small, well-modelled delays. In other words, space, from Earth's point of view, is boring in exactly the way engineers love. A G2 storm corresponds to a KP of 6. That might not sound like much on a 0 to 9 scale, but each step is not linear. Going from KP3 to KP6 is not twice as bad. It's more like going from a gentle ripple to someone leaning on the entire system with both hands. At KP6, the auroral oval swells equatorward, sometimes far enough that people in northern US states or Central Europe can see curtains of light they almost never see at their latitude. The currents flow in the ionosphere overhead. Those currents in turn induce currents in long conductors on the ground, pipelines, power lines, even the steel in railroad tracks. None of this guarantees catastrophe. We have ridden out many KP6 events without major incident. But for the systems that care, it is the difference between a normal workday and everyone pays attention now. It is the threshold where warnings change from academic to operational. And this time, that threshold is being crossed without the usual trigger, a big CME slam. When a coronal mass ejection hits, it is obvious. Upstream monitors at the L1 Lagrange point see a sudden jump in solar wind speed and density, a sharp shock, as the leading edge of the ejected plasma plows into the ambient wind. The magnetic field readings spike. Ground magnetometers register what's called a sudden commencement, a near-instantaneous jolt as the magnetosphere is compressed. Within hours, the KP starts climbing. Forecasters can point at the data and say, "Here comes the punch." What's on the way now doesn't look like that. Instead of a sudden wall of plasma, the models show a smooth but significant rise in solar wind speed over the course of many hours, from a gentle approximately 350 km per second up into the 600 to 700 km per second range. Density increases, but not in the abrupt hammer blow manner of a CME. The sun has not thrown anything at us, in the classic sense. It has opened a valve. And yet, NOAA's forecast jumps KP from quiet values near 1 up to that storm level 6 in less than a day. If you're used to the standard script, big flare, big CME, big storm, this raises an uncomfortable question. How can you get geomagnetic disturbance on par with some CME-driven events without the CME? Where is the impactor? If there is no visible blast wave, no giant plasma cloud bearing down on us, what is it that takes Earth's magnetic field from barely moving to actively storming? There is a missing piece here. Some structure in the solar wind that does not look like a classic ejection, something quieter and less obvious on images, but no less capable of twisting Earth's magnetosphere into disorder. If there is no punch, what exactly is hitting us? To understand why a hole in the sun matters, you have to start with something we almost never think about: the fact that space is not empty. The sun is not just a ball of light hanging in a vacuum. It is a machine that leaks. Every second of every day, from every part of its surface, the sun is blowing material into space. Not in discrete puffs, not only when it flares, but continuously. A faint, invisible outflow of charged particles, mostly electrons and protons, streams away in all directions. We call it the solar wind. If you could somehow stand still halfway between the sun and Earth and stretch out your hand, billions of these particles would pass through the space your palm occupies every second. They are sparse, far emptier than the best vacuums we can make in laboratories, but they are not nothing. And they are not still. Even on a quiet day, the solar wind is racing outward at hundreds of kilometers per second. Most of the time we treat this like background noise, like air pressure at sea level, like the constant low hiss of a distant highway. It's there. It does not change much. We factor it into our designs and we move on. The solar wind at Earth's orbit might cruise along at, say, 350 to 400 kilometers per second. That's about 1 million miles per hour. Fast, yes, but steady. Predictable enough that the term ambient solar wind exists at all. Earth lives inside this stream. Our planet's magnetic field pushes back against it, like carving out a protective bubble, the magnetosphere, that stands off the solar wind a few tens of thousands of kilometers above our heads on the day side, and stretches out into a long tail on the night side. If you've ever seen a picture of the magnetosphere that looks like a droplet with a long trailing tail, that's what you're seeing, the shape of a magnetic shield being sculpted by a continuous flow. That background breeze does more than shape our shield. It carries the sun's magnetic field with it. It sets the baseline conditions for everything from auroras to the way radiation belts behave. But on most days, it does so gently. The wind speed ticks along in a familiar range. The particle density holds around a familiar few particles per cubic centimetre. The magnetosphere flexes a little, then relaxes. Nothing dramatic. What's in the forecast now is not that background. The models and upstream measurements are showing a change, not a blip, not a glitch, but a ramp. Over the span of a day or so, the solar wind speed at Earth's orbit is expected to climb from that calm 350 to 400 kilometers per second up past 600, maybe touching 700 kilometers per second. On paper, that's just another number. In reality, that is the difference between a slow river and a flood. Imagine a stream flowing lazily past you. Drop a stick in it, and the stick meanders downstream. The water pushes but gently. You can wade across without much effort. Now picture that same channel after heavy rains, when the water is surging downhill twice as fast. The volume doesn't have to change much for the force on your legs to double or triple. Step into that, and you feel the difference immediately. The solar wind is like that. Its ability to shove Earth's magnetic field around depends strongly on its speed. There's a simple rule in physics that captures this. Dynamic pressure, the pushiness of a flow, roughly scales with the square of the speed. Double the speed, and you don't just double the pressure, you roughly quadruple it if density stays the same. So when the wind at Earth's orbit goes from 350 kilometers per second to 700 kilometers per second, it's not just twice as fast. In terms of the shove it can give our magnetic shield, it can be closer to 4 times as forceful. If the density of the wind rises at the same time, which often happens at the leading edge of these high-speed streams, that pressure can climb even higher. Now take that flow and remember, it's not a burst. It's a stream that can stay elevated for days. At 700 kilometers per second, a particle leaving the sun's surface takes around 2.5 days to reach Earth. But once the stream is established, once the tap is open, there is no discrete arrival and departure the way there is with a coronal mass ejections front. There's a leading edge where conditions change, and then a plateau where the wind just stays angry. From the planet's point of view, this is the difference between seeing one big wave hit the shore and watching the tide rise, then sit high for days. When forecasters talk about a high-speed stream, these are the numbers they're looking at. They see the ambient wind tootling along at 350 kilometers per second. They see an oncoming patch of wind at nearly 700 kilometers per second. And they know what that speed implies for dynamic pressure. They know that embedded in that wind is the sun's magnetic field, twisted and stretched by whatever region it came from. They know that when those conditions reach Earth, the magnetosphere will not be nudged. It will be pushed hard. This is the part that often gets lost in simplified coverage of solar storms. We talk about flares, CMEs, and when will it hit, as if the sun is normally hands-off and occasionally throws things at us. That's not the reality. The reality is that the sun has been hitting Earth continuously for as long as our planet has existed. We live in a permanent gale. Space weather is not about the presence or absence of that gale. It's about how structured, how fast, how magnetically charged that gale becomes at any given time. A flare is a flash in the gale. A CME is a gust, a big discrete gust that you can see in time. A high-speed stream from a coronal hole is something else. It is the gale tightening, focusing and not letting up. Right now, that is what's being forecast. The quiet, invisible wind in which our satellites and astronauts float is about to change character. To understand why, and why it keeps happening on a schedule, you have to look back at that dark wound on the sun and understand what it really is and what it is not. If you pull up the right kind of image of the sun right now, it looks wrong. Not the familiar yellow disk you see in cartoons. In extreme ultraviolet or soft X-ray light, the wavelength satellites like NASA's Solar Dynamics Observatory, SDO, used to study the outer atmosphere. The sun looks like a churning ball of electric blue flame. Arcs and loops of hot plasma trace out magnetic fields. Bright patches mark active regions. It is busy and structured and alive. And then, in the middle of all that glow, there's a wound. A vast, inky patch sprawled across the solar surface, breaking the pattern. Where the surrounding corona shines, this region looks almost black. Like someone has taken a cosmic ice cream scoop to the sun and carved out a chunk of light. If you didn't know better, you might think you're looking at damage, as if a piece of the sun is missing. That's why the name coronal hole is so misleading. You hear hole and your brain fills in a crater, an absence, a gap where something used to be. It suggests that material has been removed, that the sun has somehow been punctured. The images encourage that interpretation. Bright corona, dark void, easy story. But nothing is missing. The sun under that dark patch is still the same nuclear furnace it is everywhere else. Roughly 15 million degrees in the core, fusing hydrogen into helium by the ton every second, radiating energy outward through a thick, turbulent envelope before it finally escapes as light. There is no crater in the photosphere, no bite taken out of the star. What's different in a coronal hole is not the sun itself. It's the way the sun's magnetic field is arranged above that patch. Think of the corona, the sun's outer atmosphere, as a sea of hot, ionized gas. That gas is so thin and so charged that it doesn't just move where it pleases, it is leashed to magnetic field lines. Now imagine those field lines the way you would imagine the field around a bar magnet. Take a magnet and sprinkle iron filings around it. The filings align along invisible loops that emerge from one pole, arc through space, and dive into the other pole. The shape of those loops is a map of the magnetic field. On the sun, you have something similar, except the magnet is not simple. The solar field is tangled, twisted, constantly evolving as plasma churns and rotates below. In many regions, the magnetic field lines arch up from the surface and then curve back down nearby, forming closed loops, literally loops of magnetism that begin and end on the sun. Those closed loops act like cages. Hot coronal plasma gets trapped inside them, strung like beads along magnetic wires. Because it is confined, it becomes dense. And dense, million-degree plasma glows very brightly in extreme ultraviolet and X-ray. That's why, in those SDO images, most of the sun looks like a bright textured surface. You're seeing confined, glowing plasma in a cage of loops. Now picture a region where the field isn't shaped into neat, closed cages. In a coronal hole, the magnetic field lines don't loop back to the surface nearby. They rise from the sun and then keep going, stretching outward into interplanetary space. They're open in the sense that on the scales we care about, they don't return. They thread out into the solar wind and eventually merge with a broader magnetic field filling the heliosphere. No cage, no closed loop, no lid. Put hot plasma at the base of an open field line and it does the only thing it can do. It flows outward along that field, like gas escaping through a chimney. There's nothing to trap it, no magnetic bowl for it to sit in. The particles simply leak away continuously, following the path the field line lays out for them. From above, in UV or X-ray light, that region now looks dark. Not because the sun has gone missing there, but because the corona above it is less dense and cooler than its surroundings. Just with plasma spilling out along open field lines, there's simply less material left behind to emit in those high-energy wavelengths. The hole is not a hole in the sun, it's a hole in the magnetic cage. A better metaphor is not crater but exhaust vent. Think of a power plant with a huge exhaust stack. Inside the plant, heat and gases are generated in vast quantities. The exhaust stack is where the system finds a path to expel those gases. You don't say there's a hole in the plant where the stack is. You say, this is where the flow is concentrated. The chimney is the organized outlet. A coronal hole is like that. It is where the sun's outer atmosphere has found an open path to escape. Or think of a fenced field. Most of the perimeter is wrapped in strong fencing, closed magnetic loops. That animals inside that fence can mill around, bump into each other, pile up, but they cannot get out easily. And then, at one point along the fence, someone swings a gate open. Suddenly there is a path to the outside. Animals don't teleport away. They walk through the gate, one after another, in the stream. On the sun, the coronal hole is that open gate in the magnetic fence. The animals are charged particles. The stream is the high-speed solar wind. Once you see it that way, the naming starts to feel almost backwards. The hole is not an absence of stuff. It is an absence of confinement. And that difference between closed cages and open gates is what turns a random patch of the sun's surface into a source of a focused, fast solar wind stream. Closed loops, plasma stays. It gets hot. It glows. From our point of view, the corona looks bright. Open field lines, plasma drains away. The local corona thins out, emits less in EUV and X-ray, and shows up as a dark patch. But that darkness is deceiving. It is not nothing. It is motion. It is the sign that material is leaving. This is why the coronal hole linked to our current storm looks like a yawning black wound on SDO images. We're seeing the footprint of an open magnetic structure, an area where the sun's atmosphere isn't being held in place but is being funneled outward. It also explains why the outflow is not explosive. There is no single boom when a coronal hole forms, nothing like the snap of a flare. Once the field lines in that region open, the leak begins and simply doesn't stop. As long as the open configuration persists, it's not a gunshot, it's a pipe left open. The plasma doesn't need to be hurled outward by a blast. It just follows the easiest available path along the field and keeps going. From Earth's perspective, that means the solar wind coming from a coronal hole is different from the solar wind inside a CME. A CME is a one-time event, a blob of plasma thrown out and done. A coronal hole is a structure, a standing vent that will keep feeding the wind as long as it exists. And because the sun rotates, that open gate doesn't just sit still relative to us. Every 27 days or so it swings back into position, the exhaust vent lining up with Earth's orbit again, sending another fast stream down the magnetic highway that connects that dark patch of the corona to our magnetosphere. The name hole makes it sound like damage. What it really is a door that, once opened, does not slam shut after one dramatic event, but stays ajar, letting the sun's atmosphere spill into space day after day. The storm we're watching unfold now is not the story of something that exploded. It is the story of a gate that opened, and of what happens when our planet keeps drifting past that gate over and over again. Once you see a coronal hole as an open gate in the sun's magnetic fence, there is a natural next question. Where does that gate lead? Those open field lines we talked about don't just poke a little way out into space and stop. They extend. They are the scaffolding on which the solar wind hangs as it races outward, and they have direction. If you could paint the magnetic field lines anchored inside a coronal hole and watch them in 3 dimensions, you would see something like a bundle of invisible rails flowing away from the sun, carrying plasma with them. The particles don't leave in a perfect sphere. They follow those rails. In that sense, a coronal hole is not just an opening. It is the anchor point of a high-speed lane in the solar wind. A good way to picture it is to imagine a giant, slow-turning sprinkler in the middle of a field. Instead of spraying water in all directions evenly, this sprinkler has a few narrow jets, streams of water that are faster and more focused than the mist around them. As the sprinkler rotates, those jets sweep across the field. If you stand in one spot, you're not getting blasted all the time. Once per rotation, the jet lines up with you. For a brief interval, you're in the line of fire. Then the sprinkler turns, and you're back in the background drizzle. The sun is that sprinkler. The coronal hole is one of the jets. The sun spins roughly once every 27 days as seen from Earth. That number, the synodic rotation period, folds in the fact that Earth is moving around the sun at the same time. So from our vantage point, the pattern on the solar surface takes a little longer to come back into view than it would if we were standing still. Anchor a coronal hole on that spinning surface and you get a rotating source of high-speed wind. The open magnetic field lines rooted in the hole stretch out, and as the sun turns, they're dragged into a spiral shape by the combination of solar rotation and outward flow. This is the Parker spiral you sometimes hear about, the graceful spiral arcs of the solar magnetic field threading the solar system. But here's the key. Earth is not everywhere at once. We follow a nearly circular path around the sun in a thin plane called the ecliptic. For Earth to feel the full brunt of that fast lane in the solar wind, the part of the sun where the coronal hole lives has to be pointed toward that plane, toward us as it rotates. When the hole is near the centre of the solar disk from our point of view, near what's called the central meridian, its open field lines are oriented in such a way that the stream they carry is aimed squarely across Earth's orbit. The high-speed lane intersects our path. For a few days around that alignment, Earth sits in that lane. The upstream monitors at the L1 point see solar wind speed climbing. The magnetosphere feels the increased pressure. KP values respond. Auroral ovals swell. Satellites in certain orbits see their environment change. Then the sun continues to turn. The foot point of the hole rotates toward the western limb away from the direct Earth line. The fast stream is still there, pouring out of the gate, but its main thrust is no longer aimed at us. Like the sprinkler jet sweeping onward, it now passes behind Earth's position, intersecting other parts of the heliosphere. By the time the hole rotates fully out of view over the western edge, the worst of the stream has usually passed us. The solar wind at Earth's orbit settles back toward background speeds. The storm, if one was triggered, decays. Space weather reports dial back to unsettled or quiet. From our point of view, it feels episodic. A few days of elevated wind and disturbed conditions, then a couple of weeks of relative calm. From the sun's point of view, nothing so dramatic happened. The gate simply rotated past us once. 13.5 days later. If the coronal hole is still there on the far side of the sun, if its magnetic structure has survived the half rotation we couldn't see, it will begin to creep back onto the eastern limb. Solar observatories get their first hints of its reappearance in side-angled images. Models update. Forecasters check what happened last time it faced us. How fast did the wind get? How strong was the geomagnetic response? Roughly 27 days after the last alignment, the wound on the sun is back at centre stage. The jet has swung around again. The open magnetic highway anchored in that dark region once more intersects Earth's orbit. And for another few days, the invisible river pouring out of that exhaust vent will be aimed straight at our planet. This is recurrence. Unlike a flare, here and gone, or a single CME launched, we're travelled, collided, and dispersed. A long-lived coronal hole turns the sun's rotation into a schedule. So long as the magnetic configuration that creates the hole persists, each rotation carries that open gate back into view on more or less the same cadence. Some coronal holes are fleeting, appearing for a rotation or two, and then closing as the sun's tangled field reorganizes itself. Others are remarkably stable. In past solar cycles, observers have tracked individual holes for 6, 8, 10 complete rotations. That's half a year or more of repeated streams, each one a few days long, with about 24 days between peaks. If you map those events out on a calendar, you don't get random hits. You get a drumbeat. This is why when a significant coronal hole first swings onto the Earth-facing disk and proves itself capable of driving storms, forecasters start talking not just about this week, but about next month. They know that if the structure holds, the same configuration will be back approximately 27 days later. They will watch the far side data for signs that the hole is shrinking, shifting, or disappearing, but until it does, the expectation is simple: it will return. There's a strange psychological dissonance in that. On one hand, it's comforting. A chaotic universe that occasionally blindsides us with flares, and CMEs suddenly offer something clock-like. You can plan around it. You can say, last month it drove a moderate storm. Expect something similar around the same date this month, with better confidence than you can predict most individual CMEs. On the other hand, that regularity is exactly what makes it dangerous in a different way. A single storm is something you ride out. A monthly hammer is something that changes the baseline. It means your satellites, your power systems, your navigation networks are not just being tested by isolated flukes. They are being put on a schedule of stress. Every few weeks, another fast lane in the solar wind sweeps across our orbit, shouting through the background gale. This isn't a one-off explosion, it's a metronome. And the thing about a metronome is that if you're not counting the beats, if you treat each click as an isolated noise, you miss what the pattern is doing to you over time. We've talked about the open gate and the highway it feeds. We've talked about how the sun's rotation swings that highway across our path again and again. What we haven't talked about yet is what happens when that high-speed traffic doesn't flow into empty space at all, but straight into the slower solar wind already out there. Because a fast lane catching up to slow traffic doesn't just pass through politely. It piles up, it compresses, it creates a very particular kind of shock front. And that front is what actually slams into Earth. So far we've been talking about the coronal hole as if it simply turns on a fast lane in the solar wind and points it at us. The gate opens, the particles stream out at 600 or 700 kilometers per second, and eventually that faster flow reaches Earth. But there's a problem with that picture. Space near Earth is not empty when the stream arrives. It's already filled with solar wind, slower, gentler, background wind that left the sun earlier and has been cruising outward at a more relaxed pace. That slow wind got here first. It's already occupying the lane. Now imagine what happens when the fast lane catches up. Think of a highway at night. The speed limit is 60. Most cars are doing 40. Traffic is light, but it's there. A steady trickle of taillights ahead of you. Now behind that, there's a sports car doing 100. It's eating up distance quickly. The driver can see the slow traffic ahead, but the road is only one lane. You can't just teleport through the cars in front of you. What happens when that fast car reaches the back of the slow pack? It has to brake. The fast traffic slams into the slower traffic, compressing the whole stream. The cars bunch up. The distances between them shrink. If there's more fast traffic behind the first car, it also piles in. You get a dense region, a knot of vehicles moving more slowly than the fastest wanted to, but faster and more chaotically than the slowest were before. And that compression doesn't just sit there, it moves. The whole jam creeps down the highway. A moving front where density and speed are both different from the undisturbed flow on either side. That's almost exactly what happens in the solar wind. Ahead of the high-speed stream from the coronal hole, there is slow wind, the ambient outflow at perhaps 300 to 400 kilometers per second that was already on its way out when the hole turned toward us. The fast wind behind, at 600 to 700 kilometers per second, cannot overtake the slow wind and glide through it as if it weren't there. Plasma is a fluid. It interacts. When the fast wind reaches the tail of the slow wind, it pushes into it. It compresses it. Between the undisturbed slow wind ahead and the undisturbed fast wind behind, a transition region forms. In that region, everything is amplified. The particle density increases as slow and fast plasma are squeezed together. The magnetic field intensity rises as the field lines get crammed into a smaller volume. The flow becomes more turbulent, more structured, less like a smooth breeze and more like a rough, choppy sea. This structure has a name, a co-rotating interaction region, or CIR. Co-rotating because it is anchored to the coronal hole source that rotates with the sun. Interaction region because it is literally the interface where two different populations of solar wind, slow and fast, collide and mingle. From a distance, looking down on the Sun and its outward spinning spiral of magnetic field lines, a CIR is like a kink in the spiral, a ridge that curves outward from the Sun, maintaining its shape as it co-rotates with the star's rotation. On a line between the Sun and Earth, a CIR is the wave of compressed plasma that sweeps past when that ridge crosses our orbit. Here's the crucial part. When forecasters issue a storm watch for a high-speed stream event, what they're really bracing for first is not the plateau of high-speed wind itself. It's this compression front. Upstream instruments at the L1 point see it as a sudden change in conditions. The solar wind speed jumps upward, the density spikes. The magnetic field strength can double or triple in minutes. If you plot those values over time, you see a clear knee, a discontinuity, marking the arrival of the CIR. On Earth, ground magnetometers often register a sharp response shortly afterward. The magnetosphere, which had been comfortably cushioning the gentle push of slow wind, suddenly feels a much harder shove. Like a bell struck more sharply, it starts to ring. Why is the CIR so effective at driving geomagnetic activity? Two main reasons. First, pressure. As we talked about earlier, the dynamic pressure of the wind depends on both speed and density. The CIR has both. It is where the fast wind's higher speed and the compressed density of both fast and slow wind stack on top of each other. From the magnetosphere's point of view, this is where the solar wind's fist is clenched the tightest. Second, magnetism. The solar wind isn't just particles, it carries the Sun's magnetic field with it, frozen into the plasma. In a CIR, that field is squeezed, twisted and rotated by the compression and turbulence. The result is a region where the direction of the interplanetary magnetic field, the IMF, can change rapidly and unpredictably. Remember that north-south component, BZ, that determines how easily the solar wind's field can connect with Earth's field? In the smooth, slow wind, BZ might hover around a small positive or negative value for hours. In a CIR, BZ can swing southward strongly and stay there for extended periods, or oscillate rapidly, offering repeated opportunities for magnetic reconnection on Earth's dayside. That combination, high pressure plus favourable magnetic orientation, is what turns a simple increase in solar wind speed into a storm-driving engine. The CIR is the leading edge of that engine, saying the place where the slow background wind and the fast coronal whole wind actually meet and argue about who gets to occupy the space between the Sun and Earth. Behind the CIR, in the body of the high-speed stream, conditions are still elevated. The wind is still fast, the magnetic field can still be strong, and the magnetosphere can stay disturbed for days. But it's that initial arrival of the compression front that often produces the most dramatic change in a short time. The jump from a quiet KP of 1 or 2 to a storm level 5 or 6 in less than a day. If you go back to that NOAA G2 watch and ask, what are they really seeing in the models that makes them sure something is coming? This is the answer. They're not just looking at a patch of dark corona and guessing. They're looking at where the high-speed stream from that patch will catch up to the pre-existing slow wind, where the CIR will form along the Sun-Earth line, and when that moving compression front will reach our orbit. From the ground, you don't see any of this. There's no flash, no glowing wave sweeping across the sky. The CIR is invisible to your eyes. It is just numbers on a plot, a kink in time series data from a lonely spacecraft sitting 1.5 million kilometers upstream. But invisibility doesn't mean ineffectiveness. The CIR is the reason a quiet leak from a coronal hole, plasma simply draining away along open field lines, can nonetheless arrive at Earth as a sharp storm-starting hit. The gate on the Sun doesn't explode, isn't. The interaction out in space is what sharpens its outflow into a front. This is the unseen shock front that makes a quiet leak into a storm. From space, Earth looks like a simple sphere wrapped in air and clouds. But magnetically, it is anything but simple. It is wrapped in an invisible, flexible shell. That shell, the magnetosphere, is carved out of the solar wind by our planet's magnetic field. On the side facing the Sun, that field pushes back against the constant flow of charged particles, holding them off like a bow wave in front of a ship. On the night side, the wind stretches the field lines out into a long tail that trails behind us for hundreds of thousands of kilometers. It's tempting to imagine this magnetic shield as rigid, like a glass bubble. It isn't. It is more like a rubber membrane being pressed on from the outside and tugged on from the inside. It flexes, it vibrates, it can be squeezed thinner and then rebound. When the solar wind is slow and steady, the pressure on that membrane is light. The magnetosphere settles into a stable shape. The currents it carries and the electrical fields it supports are relatively small and well behaved. Down on the ground, magnetometers, essentially magnetic compasses with digital nervous systems, see only tiny wobbles around their usual baseline. In that regime, the planetary KP index hovers down at 0, 1, maybe 2. Quiet. When a co-rotating interaction region arrives, that quiet doesn't last. We talked about what the CIR looks like in space, a sharp rise in solar wind speed, density and magnetic field strength. When that compression front reaches Earth, the first thing the magnetosphere feels is a shove. Will the magnetopause, the boundary where Earth's magnetic field and the solar wind balance, gets hammered and pushed earthward. The whole structure rings. On the ground, at a network of roughly a dozen key observatories scattered across different longitudes and latitudes, this shows up as a sudden impulse, a quick deflection in the measured field as the compression wave passes through. Those observatories each compute a local K-index based on how far their magnetic needles wander, from the norm over a 3-hour window. Those local values are then combined into a global average. That average, rounded and scaled, is KP. A jump from KP1 to KP6 means that, globally, those quiet wiggles have become large, coordinated swings. The currents flowing in near-Earth space have intensified. The magnetosphere is no longer simply deflecting the solar wind, it is coupling to it. That coupling depends on more than just how hard the wind is pushing. It depends on how the wind's magnetic field is oriented relative to our own. Picture Earth's magnetic field as a series of lines flowing outward from the south magnetic pole, arcing through space and diving into the north magnetic pole, a giant bar magnet embedded in the planet. Now imagine the solar wind's embedded field sweeping past from sunward to anti-sunward, a set of lines frozen into the plasma stream, oriented at some angle in 3 dimensions. One particular component of that interplanetary field matters most for storms, the north-south component, BZ. As if BZ is pointing northward, aligned with Earth's field on the day side, those external lines tend to slide past our magnetosphere without strongly connecting. The magnetic doors between the two systems stay mostly closed. Energy still gets in, but grudgingly. When BZ flips southward, pointing opposite to Earth's dayside field, the geometry changes. Oppositely directed field lines in close proximity don't like to ignore each other. Under the right conditions, they break and reconnect in new configurations. This process, magnetic reconnection, is the fundamental way magnetic energy and plasma can be transferred between the solar wind and a planetary magnetosphere. A metaphor helps. Think of 2 zippers facing each other, teeth interlocking in opposite directions. When both are zipped up separately, they form 2 sealed systems, but if you bring them together and pull at the right angle, the teeth can cross-connect, forming a new path where there wasn't one before. The seam is no longer a barrier, it's a conduit. When Bez is strongly southward at Earth's magnetopause, the teeth of the solar wind's magnetic field, and Earth's field line up in just the right anti-parallel way to make reconnection efficient. Field lines peel back and rejoin, stitching the solar wind directly into Earth's magnetic topology. Suddenly, solar wind plasma and energy have a shortcut into our system. In a CIR, because the field is compressed and jostled, BZ can swing hard and stay south for hours. That is like taking the zipper that's normally only partly open and yanking it all the way down. On the day side, this opens a door for energy to flood into the magnetosphere, pumping up currents and stretching the night side tail. On the night side, further reconnection events occur in that tail, releasing stored magnetic energy in bursts. Those releases fling charged particles down Earth's magnetic field lines toward the polar atmosphere. From the ground, we see those particles as auroras, shimmering curtains and arcs of light where electrons and ions slam into air molecules and make them glow. In a storm with KP6 or 7, those curtains that are usually confined to the high Arctic and Antarctic expand equatorward, painting the skies over places that almost never see them. For many people, that's the only visible sign that anything unusual is happening above their heads. But while people are outside taking photos of green bands on the horizon, less photogenic things are happening too. The same currents that make the aurora glow also modify the ionosphere, the charged layer of the upper atmosphere that radio signals interact with. High frequency, HF radio, the kind that can bounce off the ionosphere and travel over the horizon, becomes unpredictable or simply unusable under parts of the auroral oval. For aircraft flying long routes over the poles, where satellite coverage can be patchy and HF is a vital backup link to air traffic control, this matters. Dispatchers may reroute flights to lower latitudes or different altitudes to maintain reliable communication, burning more fuel and time. Satellite navigation signals, including GPS, have to pass through the ionosphere twice, once on the way down to your receiver and once for the timing signal that tells your device where it is. During a geomagnetic storm, the electron density in that ionospheric layer can become lumpy and turbulent. The path the signal takes is no longer smoothly varying and easy to correct for. Instead, signals can scintillate, flicker and distort, arriving late, bent, or not at all. For your phone, this might mean your blue dot drifts or takes longer to lock on. For precision applications, agriculture, surveying, automated landings, it can mean operations have to pause. Power grids feel the storm through a different route, through Earth itself. The changing magnetic field induces electric fields in the ground, which drive currents through long conductors such as high-voltage transmission lines. Those geomagnetically induced currents sneak into transformers, biasing them in ways they were never designed to handle. Even in moderate storms, operators at higher latitudes keep an eye on their systems, ready to adjust load and configurations to prevent overheating or mistripping of protective equipment. All of this, the aurora brightening, the radios cutting out, the GPS degrading, the grids being watched a little more nervously, can unfold over the span of just a few hours once the CIR hits and the BZ tips south. From space weather is boring to the magnetosphere is snapping into storm mode in less time than a work day. And remember, in the scenario we've been tracing, this snap does not arrive in a pristine, well-rested system. The magnetosphere may have already been sitting under elevated electron flux for a week or more. The radiation belts may already be swollen. Satellite components may already be carrying a silent accumulated charge in their insulating layers. The CIR's arrival and the magnetic field's southward turn are the visible triggers. They are the punch we can see in the data. But the damage they can set off depends on how close to its limits the system was before they ever showed up. That quiet loading, that invisible pre-stress, is the part of the story most coverage skips. it is also where the shift from seeing space weather as a series of isolated storms to seeing it as a continuous pressure really begins. Up to now, we've been talking about the moment the system snaps. The CIR arrives, the solar wind pressure jumps, the magnetic field tips south, and the magnetosphere shudders into storm mode. But that moment doesn't happen in a vacuum. By the time the front actually hits, Earth's near-space environment is almost never a blank slate. It carries memory. That memory lives, in large part, in two invisible torus-shaped regions wrapped around our planet, the Van Allen radiation belts. If you could turn off the atmosphere and paint every trapped charged particle above Earth with a tiny point of light, you'd see two glowing donuts encircling the planet. One sits closer in, dominated mostly by energetic protons. The other, further out, is richer in energetic electrons. Together, they are the radiation belts, zones where charged particles are trapped by Earth's magnetic field, bouncing back and forth between the poles and drifting around the planet along magnetic field lines. The outer belt, the one that matters most for this story, lives roughly between about 13,000 and 60,000 kilometers above Earth's surface, depending on conditions. Many satellites in medium Earth orbit and some transfer orbits used to move spacecraft to higher altitudes cut right through it. Even some high elliptical orbits spend large chunks of time there. Those belts are not static shelves of particles, they breathe. When the solar wind is gentle and the sun is quiet, the outer belt can be relatively sparse at the highest energies, the electrons at the dangerous for electronics end of the spectrum. When the solar wind becomes more disturbed, when speeds increase and magnetic conditions fluctuate, the belts respond. Waves generated in the magnetosphere interact with the trapped electrons, sometimes scattering them out into the atmosphere, sometimes kicking them up to much higher energies and boosting their numbers. To track that, space weather centers keep an eye on something called electron flux. Essentially, how many high-energy electrons are crossing a given area of space per second at certain energies. You don't need the exact units to grasp the point. What matters is that there is a threshold above which satellite engineers start to worry, and that threshold is not hit only during the peak of obvious storms. In the lead-up to events like the one we've been unpacking, it is common to see the outer belt quietly charge up. For 10, 12, 14 days before the CIR even arrives, monitors in geosynchronous orbit may show the flux of energetic electrons sitting above that warning threshold almost continuously. Sometimes there are peaks, days where the numbers jump even higher for a few hours, but the more important feature is the plateau, a prolonged period where the level never really drops back to its comfortable baseline. If you prefer analogies to particle counts, think of the outer radiation belt as a gigantic capacitor wrapped around the planet. A capacitor in a circuit is a device that stores electric charge. You can add charge to it gradually, raising its voltage over time. From the outside, nothing dramatic happens as long as you stay below its rated limit. But internally, the electric fields grow, the stresses mount. Eventually, if you keep charging, you reach a point where the capacitor's insulation fails, it arcs, the device discharges, often destructively. The outer belt, under weeks of elevated electron flux, is like that capacitor being brought slowly toward its breakdown voltage. Every energetic electron that joins the trapped population, every day the flux remains high, is another tiny increment of stress on systems that have to move through that environment. The space around Earth looks the same to your eyes, but electrically it is thicker, harsher, less forgiving. By the time the CIR's leading edge is approaching, the magnetosphere might already be carrying 2 weeks' worth of this added load. That means the storm is not turning on a process from zero. It is tipping a process that has been quietly running just below a critical threshold. This is where the last kilogram metaphor comes in. Imagine a metal beam spanning a gap. Engineers have calculated that under static load, it can safely support, say, 1,000 kilograms without permanently deforming. You start stacking weights on it. 100 kilograms, 200 kilograms, 500 kilograms. The beam flexes a little, but springs back. At 900 kilograms, it's under visible strain but still holding. Then you add another 50 kilograms, then another 20. Finally, you place a single extra 10 kilogram weight on top, and with a crack, the beam fails. You could blame that last 10 kilograms. It was, after all, the straw that broke the beam. But in any meaningful sense, the failure was caused by the entire load that came before. If you had dropped that 10 kilogram weight onto an empty beam, nothing would have happened. Space weather works the same way. The CIR, with its higher speed, higher density, and often southward magnetic field, is the extra weight. It is visible, it is timed, it is what we forecast and write advisories about. But the true vulnerability of the system when the CIR hits depends on everything that has been happening in the belts in the days and weeks prior. If the outer belt has been calm with low electron flux, the same CIR might produce a modest enhancement, a storm that flares and then fades with little lasting effect on hardware. If the belt has been sitting above alert thresholds for 2 weeks, the same CIR can push it into a regime where deep charging of materials and components becomes significantly more likely. And remember that preloading is largely invisible to anyone who is not staring at space environment plots. There's no aurora to photograph when the outer belt quietly fills with high-energy electrons, no dramatic spike in the planetary KP index, no airline reroutes, no evening news graphic. NOAA may issue targeted alerts for spacecraft operators about elevated electron flux, but those are specialist advisories, not mainstream warnings. To the public, nothing is happening. Meanwhile, every satellite passing through those altitudes is flying through a storm they can't see. Over time, electrons bury themselves in insulating materials on spacecraft, building up electric fields in dielectrics and on interior surfaces. That accumulated charge doesn't necessarily discharge during the calm between headline storms. It can sit there, metastable, waiting for just a bit more energy, just a bit more flux to push it past the breakdown point. When the CIR arrives and the magnetosphere snaps into a more disturbed state, it's not just creating fresh stress, it's delivering that last inconvenient kilogram onto a beam that has already been loaded close to its limit. And the beams we're talking about here aren't abstract. They're the insulation inside thousands of satellites, the software that has to ride out bit flips without failing, the power systems that have to keep working while their components age faster than their designers expected. We'll talk about those machines directly in a moment. For now, hold on to this. By the time a geomagnetic storm watch goes out, Earth's space environment may already be primed. The risk is not just in the impact you can see, but in the quiet charge that has been building up, rotation after rotation, in the dark. If this all still feels abstract, fields and fluxes and belts and indices, bring your attention to something very concrete, the hardware hanging over your head. Right now, there are on the order of 10,000 active satellites orbiting Earth, depending on the month you check. Add in dead spacecraft, spent rocket stages, and shrapnel from past collisions and breakups, and you're looking at tens of thousands of trackable objects larger than a baseball, and an uncounted swarm of smaller fragments. It is easy to think of those active satellites as distant, exotic machines. In practice, they are part of your daily life in ways you almost never notice. The navigation chip in your phone listens to timing beacons from global positioning constellations. The ATM that handed you cash and the server that recorded the transaction use satellite timing to keep their clocks in step with everyone else's. The forecast that told a farmer when to plant or an airline when to divert around storms came from weather satellites staring down at the clouds. The video call you joined this morning might have hopped through a satellite link without you ever knowing. We've quietly built a second layer of civilization in orbit, a nervous system of cameras, clocks, radios and relays circling the planet. All of it lives inside the very environment we've just described as charging up. When energetic electrons from the outer radiation belt slam into a spacecraft, they don't politely bounce off the exterior and move on. Many penetrate. They burrow into insulating layers, circuit boards, and structural materials. Some of them stop inside those dielectrics, materials meant to keep electric fields under control. Every one of those buried charges adds a tiny increment of electric field. Over hours, days, weeks of exposure to elevated flux, those increments add up. This process is called deep dielectric charging. Deep, because the charge builds up inside the material, not just on its surface. Dielectric, because it involves insulators, the very materials the satellite relies on to separate conductors and prevent unwanted currents. From the perspective of the satellite's telemetry, nothing looks wrong while this is happening. Voltages are within spec, temperatures are acceptable, signals are clean. The spacecraft seems healthy. There is no single dramatic event to point to. Internally, the fields inside those dielectrics are growing. At some point, different for every design, every material, every geometry, the field becomes strong enough to cause a breakdown. The insulator that was quietly soaking up charge can no longer hold it. An internal path ionizes. For a brief instant, a microscopic spark bridges a gap where no current was supposed to flow. That tiny lightning bolt can do a few different things. It can flip a single bit in memory, changing a 0 to a 1 in a critical register. Many satellites are designed to detect and correct these single event upsets. They're annoying but survivable. It can partially damage a component, degrading its performance in subtle ways that show up only over time. A sensor that drifts. We are a power supply that becomes less efficient. It can short out part of a circuit permanently, taking an entire subsystem offline. A star tracker, a reaction wheel controller, a transmitter. In the worst cases, it can cascade, one failure causing overloads elsewhere, leading to a total, unrecoverable loss of the spacecraft. Crucially, the timing of that discharge does not have to line up with the peak of any particular storm. A satellite might pass through a week of high electron flux, sail through a CIR-driven KP6 event, and seem none the worse for it. The headlines move on. The space weather graphs drift back toward baseline. 2 weeks later, in the middle of a quiet period, that satellite suddenly reports anomalies, or stops reporting at all. What changed that day? From the ground, it looks like random failure. From the point of view of the materials inside the spacecraft, the answer is simpler. The accumulated charge finally found a way out. Now layer recurrence on top of that. Every 27 days, as long as the coronal hole persists, we get another high-speed stream. Every 27 days, we get another CIR, another period of enhanced coupling, another likely uptick in radiation belt flux. The outer belt doesn't have time to truly reset between these visits. The flux may drop somewhat in the days after a storm, but the baseline can remain higher than it was before. Each rotation's event starts from a slightly elevated floor. The same is true for the hardware. The charge deposited in dielectrics during one cycle doesn't all magically leak away before the next. Some drains off, some remains, so when the next round of high-energy electrons washes through, it's not charging from 0. It's adding more stress to an already loaded system. Picture thousands of satellites, each with its own internal charge budget and breakdown threshold, being slowly, intermittently driven toward that threshold by a metronome in the sun's corona. The single failure of a weather satellite or a commercial communications bird is inconvenient and expensive, but rarely existential. Operators may have spares in orbit or on the ground. Networks reroute. Services degrade but don't vanish. What's new in this era is that many of our most important space systems are not single satellites. They are constellations. Starlink, OneWeb, and other low Earth orbit broadband systems are meshes of thousands of nodes, as each talking to its neighbours. GPS and its counterparts are constellations of timing beacons that together provide global coverage and redundancy. Earth observation fleets are increasingly distributed swarms of smaller satellites rather than a handful of large flagships. The resilience of a constellation comes from numbers and redundancy. If one node fails, others can take up the slack. But that same interconnectedness means that if many nodes fail in a correlated way, clustered in time or in orbital region, the network can degrade rapidly. Think about GPS. The accuracy of your location fix depends on how many satellites your receiver can see and how well their internal clocks agree. The system is designed with margin, multiple orbital planes, overlapping coverage, and ground control segments constantly updating and adjusting. Losing a single satellite is annoying but planned for. Now imagine a scenario, not tomorrow, not necessarily this year, but somewhere down the line, where repeated cycles of elevated radiation slowly push several aging GPS satellites closer and closer to their individual failure points. Their dielectrics are more stressed than when they were launched. Their components have seen more cumulative radiation than their original designers modelled. Most days, nothing happens. Then, around one particular rotation of a long-lived coronal hole, you get another extended episode of high electron flux. For some of those satellites, that is the extra dose that pushes an already weakened component over the edge. Maybe it's a clock module in one, a power regulator in another, an attitude control unit in a third. Each failure looks, on paper, like an isolated incident. But from the system's point of view, the effect is clustered. Redundancy shrinks. Positioning accuracy erodes in certain regions. Receivers that once saw 10 healthy satellites now see 7, with a couple reporting degraded signals. For a casual user, this might mean a little more drift on a map. For high-precision users, surveyors, farmers running centimetre-accurate tractors, financial systems depending on nanosecond timing, it could mean falling below the accuracy they require. For aircraft in certain approach procedures or ships in narrow channels, it could cross the line from acceptable to risky, and that's just one constellation. Apply similar logic to broadband meshes. If a cluster of low Earth orbit comm satellites sharing similar orbits and design ages all cross their fatigue thresholds, within a few months of each other, coverage gaps can open. Ground users see more dropouts, higher latency, reduced bandwidth. Companies scramble to launch replacements faster than planned, driving up costs and straining launch capacity. We don't have good public numbers on how often deep dielectric charging has already caused near misses. Satellite operators don't issue press releases for every anomaly that self-recovers after a reboot, or every subsystem that has to be turned off early. Much of what we know comes from case studies, technical conferences, and hints in the data. What we do know is that as the sky has filled with more machines, so as the opportunities for cumulative space weather stress to matter have multiplied, and unlike a single spectacular storm that knocks out a famous satellite and prompts an investigation, this kind of slow cooking is easy to miss. Each failure is a story about one spacecraft, one bad day. The pattern behind it, the monthly marinade of high-energy electrons driven by a recurring wound on the Sun, rarely gets mentioned. But the pattern is there. Every 27 days the metronome ticks. Every 27 days the orbital capacitor charges a little more. The question is not whether any single satellite can survive that. Many can. The question is what happens to a civilization whose critical spaceborne systems are all aging under the same slow rhythmic stress. And to see that, we have to look not only at the machines above us, but at the systems on the ground that depend on them. Systems that start to feel this quiet strain long before anything dramatic fails outright. So far, this story has lived mostly above the atmosphere, in solar wind streams, magnetic fields, radiation belts, and satellites quietly aging in orbit. It would be easy to file it away as space stuff. Interesting, maybe, but not something that reaches down into your daily life. It does. The first place it shows up is in something almost everyone in a modern society uses, even if they never think about it: satellite navigation. GPS and its cousins, Europe's Galileo, Russia's GLONASS, China's Beidou, work by sending exquisitely timed radio pulses from satellites high above the Earth down to receivers on the ground. Your phone, your car, a ship at sea, a tractor in a field, they all listen to those pulses, compare arrival times from multiple satellites, and solve for their position and time. Those pulses don't travel through empty space. On their way down, they have to cross the ionosphere, a layer of the upper atmosphere between roughly 80 and 1,000 kilometers altitude, where solar radiation has stripped electrons from atoms, turning the air into a plasma. Under quiet conditions, the ionosphere is relatively smooth. Its electron density varies in ways we understand well enough to correct for. GPS receivers and ground systems apply models and corrections to undo the delays the plasma introduces. The result is the seamless experience you're used to. A blue dot on a map that settles onto the road you're actually driving on. A plane on final approach that knows where the runway is within a few meters. During a geomagnetic storm, that layer stops being smooth. Yet energy dumped into the upper atmosphere by the snapping magnetosphere sets up travelling disturbances. The electron density can become patchy, forming structures and irregularities that move and evolve over minutes. Radio waves passing through those regions can be delayed unevenly, bent or scattered. At the receiver, the signal can flicker, its phase and amplitude jittering in ways the usual corrections don't fully anticipate. To you, that looks like a GPS fix that takes longer to converge, jitters or jumps. Instead of a few meters of error, you might see tens of meters. For casual navigation, that's an annoyance. For systems that have grown used to centimeter-level precision, autonomous tractors laying down seeds in laser-straight rows, survey instruments establishing property boundaries, construction crews placing critical infrastructure, it can be a showstopper. Operations halt, work is rescheduled, and GPS is not just about where you are, it's about when you are. Those timing pulses are the heartbeat for a vast swathe of infrastructure. Cellular networks use them to keep towers in sync. Financial exchanges use them to timestamp trades. Power grid control systems use them to line up alternating current phases across long-distance transmission lines. When geomagnetic storms degrade GPS timing, the knock-on effects can spread far beyond maps. Backup systems exist, ground-based clocks, fiber-optic time transfer, but they're unevenly deployed. Every time space weather pushes GPS into the unreliable zone, those backups get tested. Then there is the power grid itself. When a geomagnetic storm distorts Earth's magnetic field, the change over time induces electric fields in the ground. Those fields drive currents through long conductors at the surface, oil pipelines, train rails, and crucially, the high-voltage transmission lines that knit together regional power systems. These geomagnetically induced currents, or GICs, don't look like the normal alternating current the grid is built to carry. From the transformer's point of view, They're closer to a slowly varying direct current superimposed on top of the AC. The DC component pushes the magnetic cores of transformers towards saturation. Saturation means the core is no longer responding linearly. It's being driven to its limit. In that state, transformers can overheat and vibrate. They can generate harmonics that confuse protective relays, triggering unnecessary trips. In extreme cases, like the storm that knocked out Hydro-Quebec's grid in March 1989, a surge of GICs can lead to widespread blackouts and even permanent damage to large, expensive transformers. Events on that scale are rare, but you don't need a 1989 class storm to have consequences. Even moderate storms that never make the news can produce smaller GICs that, over and over, heat transformers slightly above their design expectations. Each event is survived. None cause obvious damage. Insulation ages a little faster. Mechanical stresses accumulate. The effective lifespan of those multi-ton pieces of hardware shrinks. Replacing a single extra transformer a decade early is an expense. Replacing many, across a high-latitude grid that sees dozen mild to moderate storms every year for years in a row, is a budget problem. Accelerated wear and tear driven by recurring coronal hole streams doesn't show up as space weather damage on a balance sheet. It shows up as higher maintenance costs, more frequent replacements, more outages blamed on equipment failure. Aviation feels the stress from above in a different way. Long-distance flights, especially those crossing polar regions, have historically relied on high-frequency HF radio to stay in touch with air traffic control and operations centres. HF signals can travel over the horizon by bouncing off the ionosphere. When geomagnetic storms pump energy into the polar ionosphere, they can turn it into an absorbing layer instead of a reflective one. Your radio waves that would normally skip across its surface now get sucked in and vanish. During such radio blackouts, aircraft on polar routes can lose their primary long-range communication channel. Airlines have to decide: accept degraded comms for a period, rely more heavily on satellite links that may themselves be affected, or reroute airplanes to lower latitudes and altitudes where the ionosphere is less disturbed. Rerouting is safer, but it comes with a price tag: longer routes, more fuel burn, more crew hours, disrupted schedules. One such storm is a blip in quarterly numbers. A pattern of monthly disturbances over several years becomes a line item executives have to care about. None of this has the drama of an entire continent going dark. It is incremental. A farmer loses a day of planting here and there because the GPS-guided tractor can't get a reliable fix during a storm. A survey project slips its timeline. An airline's fuel costs tick upward over a quarter because they had to avoid polar routes 5 times instead of once. A grid operator budgets for more frequent transformer maintenance. A telecom company invests in terrestrial timing backups after one too many GPS glitches. On their own, these are manageable adjustments. The system absorbs them. The important thing is that they're all being driven quietly by the same repeating pattern in near-Earth space. That metronome in the sun's corona sending streams past us on a 27-day schedule. Every rotation the coronal hole lines up with Earth, the ionosphere gets stirred, the transformers get nudged, either the aviation planners get another headache. The GPS receivers see more scintillation, not catastrophically, just enough to chip away at margins. This is what death by 1,000 cuts looks like in infrastructure. Not one headline-grabbing storm that takes us back to the 1800s, but a series of moderate events that gradually erode reliability and resilience. Systems designed around the assumption that serious disturbances are rare outliers instead find themselves operating under a low-level but persistent background of interference. And because each cut is small, it's easy not to connect them to each other, to blame them on aging hardware, on random glitches, on bad luck. To fix the symptom and ignore the pattern is where the risk really lives. We've been framing that pattern in terms of the spaces above us, belts of particles, streams of wind, fields snapping and reconnecting, but those are only half the story. The other half is what happens when you overlay that recurring space-driven stress on top of all the other pressures our infrastructure is already under. Roads and bridges face heavier traffic. Grids are adapting to new loads from electrification. Communications networks handle ever more data. Climate change is intensifying heat waves and storms. Now add a repeating, under-acknowledged layer. Every few weeks, the space environment gets a little more hostile for a few days. Satellites inch closer to their design limits. GPS gets a little flakier. Grids see a bit more induced current. Airlines reroute a few more flights. The danger is not just in any one of those sectors. It's in the fact that they're all chained together, and they're all being tugged, quietly, by the same wound on the sun. To see where that leads, we have to zoom out again. Not just in space, beyond Earth's protective bubble, but in time, out over the solar cycle and into the years when coronal holes, not single explosions, will define the way our star presses on the technological world we've built. Up to this point, we've been standing under a kind of umbrella. Earth's magnetic field, for all its flexibility and quirks, is a shield. The magnetosphere and the atmosphere together take the brunt of most of what the sun throws at us. They shunt charged particles around the planet, trap many of them in the radiation belts, and bleed off energy in auroras and currents high above our heads. Most of the hardware we've talked about, GPS satellites, weatherbirds, broadband constellations, flies inside that umbrella. So do the astronauts on the International Space Station. At roughly 400 kilometers up, the ISS is still deep under the magnetosphere's protection. It dips through the weaker inner fringes of the radiation belts in places like the South Atlantic anomaly, but for the most part, it's shielded from the harshest particle fluxes. The station crew's radiation doses are higher than those on the ground, but they're within bounds we understand. We have decades of dosimeter data, biological studies and operational experience with that level of exposure. Missions are planned around it. Now take a step outward. Go beyond low Earth orbit, beyond the main body of the magnetosphere, into the region of space between Earth and the Moon, cislunar space. Out there, the umbrella thins and eventually ends. The magnetic field lines stretch into a long tail, and then merge with the solar wind. There is no continuous bubble of protection. Spacecraft and humans travelling there are exposed much more directly to whatever the sun is doing. This is not hypothetical anymore. NASA's Artemis program is actively testing hardware and flight profiles for returning humans to the Moon. Uncrewed Artemis missions have already looped out beyond the Moon's orbit and back. Commercial lunar landers and orbiters are beginning to populate cislunar space. Plans for lunar gateways, surface bases, and eventually Mars-bound ships all assume that we will have people and hardware spending weeks, months, or even years beyond Earth's magnetic umbrella. In that environment, the recurring fast streams from coronal holes are not just space weather for satellites. They're the background climate you live in. The radiation environment beyond the belts has two main components: galactic cosmic rays, high-energy particles from outside the solar system, and solar energetic particles from our own star. Now, cosmic rays are always there, modulated slowly by the solar cycle. Solar particles arrive in episodes, sometimes as short, intense bursts from flares and CMEs, sometimes as elevated fluxes associated with high-speed streams. Most of our human radiation data in space comes from two regimes: low Earth orbit, under the magnetosphere, where trapped belt particles dominate and shielding gets a big boost from Earth's field. The Apollo missions, which were short, a few days in translunar space, a few days on the surface and then back. Those missions didn't happen during a period dominated by recurring coronal holes driving high-speed streams at the cadence we're discussing now. We have instruments that have measured the radiation environment in deep space for years. We can model dose rates behind various thicknesses of shielding, but we have very little direct biological experience with humans living for long durations outside the shield, while the Sun is in a mode where a particular coronal hole sends a stream our way every month. On a practical level, here's what that means. Imagine you're an astronaut on a future lunar gateway, a small outpost orbiting near the Moon. The habitat has shielding designed to reduce your exposure to cosmic rays and solar particles. On top of that baseline, mission planners have contingency plans for big solar particle events, high-dose bursts from flares, and CMEs. If instruments see one of those coming, you retreat to a more heavily shielded storm shelter, ride out the spike, and then return to normal operations. There's now a recurring high-speed stream pattern over that. Every 27 days, the solar wind speed at your altitude climbs. The magnetic field carried by that wind changes. The flux of certain particles, especially at lower energies, rises. It's not the same as a massive solar particle event. Doses are lower, but it lasts longer. For 3, 4, 5 days each cycle, your radiation dosimeters tick upward more than usual. Then things ease off. Then, a month later, they do it again. For a one-off mission, this is just another operational wrinkle. You might choose launch windows that avoid the worst alignments. You might plan EVAs, spacewalks, away from expected peaks. The extra dose is folded into your margins. For a permanent or semi-permanent presence beyond the magnetosphere, recurrence matters more. The difference between you get a storm every couple of years and you get several moderate enhancements every year on a schedule is not just a design detail, it's a lifestyle, it's a chronic condition. Biologically, chronic low to moderate radiation exposure is a different problem from a handful of acute spikes. The risks, cancer, degenerative diseases, potential cognitive effects, depend on total dose and dose rate, but the details are complicated. Shielding that is adequate for brief Apollo-style excursions may not be optimal for years-long habitation. Patterns of cell damage and repair, of DNA mutation and misrepair, are not linear functions of dose. For Artemis-era mission planners, that's a moving target. Designing spacecraft and habitats for a radiation environment that may be more lumpy and more persistent than the one we sampled in the late 1960s and early 70s. The hardware story changes too. Deep space probes and cislunar infrastructure won't be passing in and out of the belts the way today's GPS or geosynchronous satellites do. They'll be bathing constantly in whatever the solar wind is doing at 1 astronomical unit and beyond. Recurring high-speed streams mean recurring episodes of enhanced charging and discharging, not just on surfaces but throughout volumes of material. A lunar gateway that sees the same stream every 27 days has to be designed not just for the peak of any one hit, but for a multi-year pattern of them. We are, in other words, about to start living and working in an environment where the story of a hole in the sun that keeps pouring out fast wind is not just a story about how fragile our robots are. It is a story about how we manage ourselves in a place where the sun's slow, rhythmic behavior can add up in human bodies as well as silicon. We know enough to know this is not a reason to stay home. We sent people to the moon with far less data than we have now and brought them back. We will go again. We will go farther. But as we go, the details of what the sun is doing, how often, how persistently, in what patterns, matter more than they did when we were content to orbit safely inside our magnetic umbrella. A recurring coronal hole turning the 27-day solar rotation into a radiation metronome is not just a technical curiosity, where it is a boundary condition on human expansion, and we're still filling in the map. The same underappreciated metronome that is slow-cooking satellites and nudging power grids on Earth is also setting the rhythm for the future of human spaceflight. To see how long this rhythm is likely to last, and why it may only be getting stronger in the coming years, we have to look at the bigger cycle our star lives by. Not 27 days, but 11 years. So far we've been talking about a wound on the Sun and the 27-day metronome it drives, as if that wound existed in isolation. It doesn't. It's part of a larger rhythm our star has been keeping for as long as we've been watching it. Roughly every 11 years, the Sun's magnetic activity rises and falls in a cycle we've numbered and tracked for centuries. We are currently in solar cycle 25. It began when the last one, cycle 24, bottomed out. Sunspot numbers dropped to near zero. Flares were rare, and the corona looked comparatively bland. Since then, activity has climbed. More sunspots, more flares, more eruptions. At some point, around the time you're watching this, or not too far from it, the cycle reaches its peak and then starts to decline. Pinpointing the exact moment of maximum is tricky. You only know for sure after the fact when the data have piled up. But the broad pattern is clear. The Sun does not stay at maximum forever. It climbs, it peaks, and then it rearranges itself on the way back down. The way it rearranges itself matters for us, because the kind of trouble the Sun gives us on the way up is not the same as the trouble it tends to give us on the way down. In the rising phase, coming out of minimum toward maximum, the most obvious signs of solar mischief are active regions, dark sunspots clustered into complex magnetic knots that spawn flares and coronal mass ejections. The corona around those spots is bright and peppered with loops. The high-latitude regions near the poles may host coronal holes, but those holes aim most of their fast winds above or below the ecliptic plane, missing Earth. Geomagnetic storms in this phase are often CME-driven. You get sporadic but sometimes spectacular punches, big flares, big plasma clouds, big 1 or 2 day disturbances. They make headlines precisely because they are discrete events. Something explodes. It either hits us or it doesn't. As the cycle turns over and the Sun slides into its declining phase, the personality of the corona shifts. Active regions become less frequent. The rate of large flares and CMEs starts to drop off from its peak. The Sun's global magnetic field, this deep underlying structure that takes 11 years to twist itself inside out and back again, begins to simplify. And as it simplifies, something specific tends to happen to coronal holes. They grow and they move. During the rising and peak phases, the most persistent coronal holes tend to hug higher latitudes, forming dark caps near the poles. Their open magnetic field lines guide fast wind out into space above and below the plane of Earth's orbit, where it does little to our magnetosphere. We see the edges of those streams sometimes, but they're not usually the main drivers of geoeffective storms. In the declining phase, those polar holes can start to stretch toward lower latitudes. New coronal holes can open nearer the solar equator. Some structures span a wide range of latitudes, their open fields crossing the ecliptic cleanly. In extreme cases, you get trans-equatorial holes, dark regions that reach across the Sun's middle and are almost perfectly positioned to send their high-speed streams straight along the roads we travel. Those low-latitude and equator-straddling coronal holes are incredibly good at pointing their open magnetic highways at Earth. And because the underlying magnetic field of the Sun is quieter in terms of explosive reconfiguration, they can persist. Rotation after rotation, they come back. The metronome ticks louder and more regularly. Statistically, that means the declining phase of a solar cycle tends to see more frequent high-speed stream events from coronal holes compared to the rising phase. The number of extreme, CME-driven, once-in-a-decade storms might go down, but the number of moderate, recurring, stream-driven storms can go up. We are, in other words, shifting from a regime where space weather risk is dominated by rare punches to one where it's dominated by persistent floods. The wound we've been following across the Sun, the equator-ward coronal hole aligned so well with Earth that its stream has already hit us multiple times, is almost certainly not an oddball. It is a preview of the rules the declining Sun plays by. On the way up the cycle, engineers and planners lose sleep over the monsters, the Carrington-class CME that might, if it hit just right, cause serious damage in a single global event. Standards are written around those worst-case blows. Reports talk about 1-in-100-year storms. It's a very human way of thinking. Worry about the rare, catastrophic punch. On the way down, a different question quietly becomes more important. How does your system handle being leaned on, gently but insistently, every few weeks for years? A power grid hardened against the nightmare of a single extreme G5 storm might still not be optimized for the reality of dozens of G1 and G2 storms every year, eating into transformer lifetimes. A satellite designed with enough shielding to survive a handful of big solar particle events in its design, life might not have been tested against the specific pattern of repeated, moderate charging episodes imposed by recurring streams. A GPS-dependent precision agriculture operation might have plans for a once-in-a-decade day without good positioning, but not for losing several key days in multiple planting seasons back-to-back. It's not that the punch model becomes irrelevant. CMEs don't vanish in the declining phase, big ones can still happen, but the baseline changes. The lull between opportunities for the Sun to stress our systems shrinks. The quiet times get noisier. To be fair, predicting exactly how cycle 25 will behave on its way down is not something anyone can do with certainty. The Sun has a habit of surprising us. Past cycles have shown double peaks, extended plateaus, or asymmetric declines. We will only know what this one really did after we've watched it play out and counted the events. But we know the general tendency. We know that in past cycles, extended, geo-effective coronal holes became more common and more important drivers of storms as the cycle waned. We know that the shift from CME-dominated to stream-dominated geomagnetic activity is a recurring theme. And we know that our infrastructure, much of which has been launched or built in the last decade, has grown up under the assumptions of the rising phase. Most of the satellites now forming dense constellations in low Earth orbit were conceived, designed, and tested during a time when headline space weather events were still mostly associated with flares and CMEs. When you asked, what's the worst the Sun can do, the answer you planned for was a giant explosion that might hit once in the system's lifetime. The regime we're entering over the next several years asks a different question. What happens if the Sun doesn't need to hit you once very hard, because it can tap you on the shoulder every month, over and over, while you age? The coronal hole we've been tracking is a localized expression of that question. It's a specific gate in a specific cycle, turning the 27-day solar rotation into a schedule of stress for Earth. It ties all the physics we've walked through, open field lines, CIRs, preloaded belts, charging satellites, nudging grids, into a repeating pattern, and it's not done. To understand just how far that pattern can reach, across months, across orbital shells, into operational planning and budgeting, you have to think not only in terms of what the Sun is doing, but also in terms of how we count. Do we keep reacting to each event as if it were an isolated punch? Or do we start adding up the hits and realizing we're living in a flood? That shift in mindset, from episodic to continuous stress, is the real new rule of the declining Sun. And the longer this particular coronal hole, and others like it, stick around, the more urgent that rule becomes. Once a coronal hole has shown itself to be geo-effective, once it's produced a measurable high-speed stream and a real geomagnetic response, forecasters start treating it less like a one-off curiosity and more like a scheduled event. Recurrence forecasting is, in some ways, the most straightforward kind we have in space weather. It doesn't require you to predict when a magnetic knot on the sun will suddenly explode. It asks a simpler question. Does that coronal hole survive one full solar rotation? And if so, what happened the last time it faced us? The process looks something like this. A dark region appears in EUV images on the eastern limb of the Sun. Over a few days it rotates across the disk. Models estimate its size and location relative to the solar equator. Around the time it crosses the central meridian facing Earth most directly, upstream monitors at the L1 point start to see changes, rising wind speed, the telltale signature of a co-rotating interaction region, an uptick in geomagnetic activity. The event plays out. KP climbs and falls. Electron flux in the outer belt responds. Satellite operators log anomalies. Grid and aviation planners check space weather off this week's list of concerns. Then the hole continues westward and disappears over the limb. For roughly 13.5 days, it's on the far side of the Sun from Earth's point of view. We can't see it directly, but helioseismic techniques and spacecraft parked off the Sun-Earth line can sometimes give us hints about what's happening over there. Is the hole shrinking, growing, splitting, holding steady? When it reappears on the eastern limb after one full 27-day synodic rotation, forecasters compare what they see to what they logged a month earlier. If the structure looks similar in size and latitude, and if nothing dramatic has reconfigured the global solar magnetic field. In the meantime, the expectation is, we're about to get another stream, not a guess. A projection grounded in a literal previous pass. The timing may shift by a few hours. The peak wind speed and exact geomagnetic response may differ somewhat. But as long as the recurrence engine is intact, a long-lived coronal hole robust enough to survive multiple turns, the Sun has, for all practical purposes, put its intentions on a calendar. In the old, flare-centric way of thinking about solar risk, this might sound almost comforting. Predictable is preferable to random. If you know, within a day or so, that your grid, your satellites, your polar flights will be under extra stress mid-month, you can plan. That is true, up to a point. The complication is that this is not a one-and-done affair. A stable coronal hole can keep generating these scheduled streams for 6, 8, 10 rotations, half a year, or longer. Living with a 27-day metronome isn't just a figure of speech, it's an operational reality. Picture a year like this. January. The coronal hole is first noticed as a large equatorward dark patch. It rotates into alignment, sends a high-speed stream our way, and drives a G2 storm. NOAA issues a watch. Aurora photos go mildly viral. Satellite operators log a few minor anomalies. One commercial bird glitches and reboots. Power grids at high latitudes report elevated geomagnetically induced currents, but no major issues. February. The hole comes back. This time the stream arrives a bit faster. The CIR is a little sharper. KP peaks at 6 again, maybe briefly 7. Electron flux, which never fully returned to its pre-January baseline, surges higher. A couple of older satellites in geosynchronous orbit exhibit odd behavior weeks later. Investigations quietly flag space environment as a possible contributing factor. March, third rotation. The recurrence is now clear. Forecast centers speak confidently of a recurrent coronal hole, high-speed stream. Another series of moderate storms. A few more polar flights get rerouted. A regional grid, already stressed by winter load, has to manage a bit more GIC than usual. Nothing breaks. Budgets take a small hit. April through June. The pattern continues. Each month brings a few days of elevated wind speed, energetic particle flux, and geomagnetic disturbance. The exact peaks vary, Some rotations are weaker, some a bit stronger, but the cycle holds. Meanwhile, no one is hitting a giant red button marked Space Weather Emergency. Each individual event fits comfortably inside the design envelopes and contingency plans. Now, zoom out. Over those 6 months, the outer radiation belt has spent more time energized than quiet. Satellites in certain orbits have accumulated more deep dielectric charge and radiation damage than in a typical half-year. Transformers in high-latitude grids have seen repeated small bouts of extra heating and stray current. GPS users in certain regions have experienced more frequent days of degraded accuracy. Airlines have burned more fuel on rerouted flights than their pre-launch models anticipated. None of that looks like a catastrophe in isolation. It looks like fatigue. Engineers know fatigue well in the context of physical structures. A metal beam loaded to 50% of its yield strength once will not fail. Load it to 50%, release, load again, thousands or millions of times, and micro cracks begin to form. Those cracks grow. Eventually, the beam fails, not because any single load exceeded the nominal limit, but because the repeated stress altered the material itself. Our space-age infrastructure is subject to analogous fatigue. Electronic components accrue damage from repeated radiation hits, even when no single event is catastrophic. Software and firmware accumulate workarounds and patches for intermittent anomalies, adding complexity and potential new failure modes. Grid components age faster under many small geomagnetic insults than under fewer, larger ones. Operational organizations, airlines, satellite constellations, grid operators burn through margin in budgets, fuel, and staff time, dealing with small disturbances that are only small when viewed one at a time. These are all threshold systems. They can absorb stress up to a point. You can bump them, repeatedly, below their official limit, and from the outside they appear to spring back. Until, one day, they don't. That day doesn't have to coincide with the largest storm in the sequence. It might be a completely average rotation of the coronal hole. KP peaks at 5 or 6. Auroras are nice but not historic. The forecast called it well, and yet during that event a particular transformer that has survived dozens of similar currents finally fails. Or a cluster of satellites that have been carrying latent damage from years of space weather finally cross internal thresholds in the same month. From the narrative vantage point we prefer, one cause, one effect that looks unsatisfying. We want to say, this storm caused that blackout, or that event killed that satellite. In many cases, the honest answer is murkier. The last storm was simply the final straw in a stack of dozens. That's what it means to live with a metronome instead of a random drum roll. For forecasters, the recurrence engine is a gift, a rare, relatively predictable driver in a chaotic environment. For operators, it is both an opportunity and a stress. You can plan for the days when space will be less friendly, but you also have to accept that those days are going to keep coming back as long as the coronal hole survives. For the rest of us, it presents a challenge of perception. As long as we think in terms of isolated storms, we will keep underestimating what a year, or a decade, of moderate recurring disturbances can do. As long as we fail to add up the monthly hits on satellites, grids, and navigation systems, we will keep being surprised when something that has never failed before suddenly does. And complicating all of this is a simple, uncomfortable fact. We're not watching this play out with perfect information. Our ability to see the recurrence engine clearly, to track its streams, measure their impacts, and quantify the fatigue they induce, is limited by the tools we've put in place to watch the sun and the space around Earth. Those tools are good. They are better than anything humanity has ever had. But they are not complete. Some are old, some are blind in important directions, and some of the most important quantities, the ones that would tell us exactly how close to various thresholds we really are are the ones we still struggle to model or measure well. To understand how that ignorance shapes our response to a ticking solar metronome, we have to turn briefly from the sun and the storms it drives to the instruments and models we depend on to see them coming. Everything we've talked about so far, the wound on the sun, the open magnetic highways, the CIR front, the preloaded radiation belts, the 27-day metronome, relies on a simple assumption that we can actually see what's happening. Not with our eyes, obviously. With instruments, spacecraft staring at the sun, monitors sitting upstream in the solar wind, magnetometers on the ground quietly tracing the twitching of Earth's field. For the first time in human history, we have a global space weather observing system. It is good. It is also incomplete, aging in places and in some critical ways half blind. Start with the front line. The upstream monitors at the L1 Lagrange point, about 1.5 million kilometers sunward from Earth. Spacecraft parked near L1 sit in the solar wind flow between the Sun and Earth. They measure the speed, density, temperature, and magnetic field of the plasma streaming past them. When a CIR or CME is on its way, they feel it first. Their readings give us a precious 20 to 60 minutes warning before those same conditions hit our magnetosphere. Right now, that job is done mainly by a small number of craft, veterans like ACE and DSCO-VR. They were not built yesterday. They were launched into an environment no one expected to be managing constellations of 10,000 satellites and grids stretched to their limits by climate and electrification. Their instruments have aged, their sensors have quirks, and in recent years, space weather forecasters have had to contend with odd spikes, dropouts, and anomalies in the very data they depend on. When you see a plot of solar wind parameters that suddenly jump or jitter unexpectedly, there is always a moment of doubt. Is this space changing, or the instrument? Good science can usually tell the difference, but not instantly, and not always cleanly. Meanwhile, advisories have to be written. Operators have to decide whether to act. Even when the data are perfect, the warning time they provide is short. Half an hour between "we know the CIR is here" and "Earth's magnetosphere is now feeling it" is enough for some actions. Flipping a satellite to a safer mode, adjusting grid configurations, delaying a polar flight by an hour. It is not a comfortable margin for bigger decisions. There are plans on paper to improve this picture. New monitoring missions to L1. Additional spacecraft placed at other vantage points like L5. A point trailing Earth in its orbit that would give us a side-on view of the Sun's surface and the solar wind structures rotating toward us. Those missions have timelines, budgets, and competing priorities. Until they fly, we rely heavily on a few aging eyes. Move closer in to the Sun itself. We have excellent solar observatories, SDO in geosynchronous orbit, SOHO at L1, stereo spacecraft giving us off-angle views when they're positioned well. They feed us constant streams of images in multiple wavelengths. That's how we spot the coronal holes. That's how we watch active regions grow and decay. But they only ever see the near side of the Sun directly. The far side, half of the star's surface at any given time, is inferred. Heliosseismology can tell us where big active regions are hiding by watching how waves propagate through the Sun's interior. Some off-angle views from spacecraft not on the Sun-Earth line can fill in patches, but we don't get the same detail for the far side that we do for the front. So when a coronal hole like the one we've been talking about disappears over the western limb, we can't watch, in real time, exactly how it evolves on the far side. We infer. We project. We assume that if it's been stable for several rotations, it's likely to still be there next time. Most of the time, that's good enough. Sometimes it's not. Then there are the models. Space weather models take in solar observations, upstream solar wind data, and our best understanding of plasma physics and magnetic fields. and try to predict what will happen next. They are sophisticated, and they have improved dramatically over the last couple of decades. They can tell you roughly when a CIR will arrive and how strong the shock might be. They can estimate KP ranges, probabilities of storm levels, likely durations. What they struggle with are precisely the things that matter most for fine-grained risk. The exact timing of southward BZ intervals, those windows when the solar wind's magnetic field is oriented just right to connect strongly with Earth's. The detailed internal structure of CIRs and high-speed streams, especially when multiple streams and CMEs interact. The multi-rotation evolution of individual coronal holes. Will this one shrink, grow, split, merge with another, or drift in latitude over the next 3 months? For a news headline, moderate storm possible late Tuesday. These uncertainties don't seem like a big deal. For a satellite operator deciding whether to delay a delicate maneuver by 24 hours, or a grid planner weighing multi-billion-dollar investments in mitigation equipment, they matter. Now put those observational and modelling limits next to the decisions we're making. We're designing constellations of thousands of satellites with assumed radiation environments and anomaly rates baked into their business models. We're building out high-voltage transmission lines to move renewable power across continents, with certain expectations about how often they will see GIC-inducing storms. We're writing standards for aviation communications, maritime navigation, emergency response systems, all of which depend, somewhere in the chain, on space-based assets and timing. All of that planning rests on historical data and models that may not fully capture what a declining phase, stream-dominated sun can do to a hyper-connected, satellite-saturated civilization. We can count how many big storms past cycles produced. We can tabulate how many KP5 and above days occurred in a decade, but we have very few long continuous records that integrate cumulative stress, the way a satellite or transformer actually experiences it. We don't, for example, have a widely used metric that says, over the past 5 years, the outer radiation belt has spent X% more time above this hazardous flux threshold than the previous 5 years, or high-latitude transformers have cumulatively seen Y% more GIC-inducing hours this cycle than last. Those are the kinds of integrated measures that would tell you whether your existing hardware is aging faster than its design assumptions. Instead, much of our accounting is still event-based. How many storms exceeded a certain KP? How many days had certain conditions? That's useful, but it misses the slow cooking. To be clear, none of this means we're flying blind. We're not. Space weather centres around the world do heroic work with the data and tools they have. Forecast accuracy for many parameters has improved significantly over the last couple of cycles. Researchers are constantly refining models, assimilating more observations, testing predictions against reality. But there is a gap between what we'd ideally like to know. How close to various fatigue thresholds are our satellites really? How much shorter is the average transformer lifetime in a recurrent stream environment? And what we can actually say with confidence. And sitting in that gap are very real choices. How much extra shielding is worth it on a satellite that has to be cheap to launch by the 1,000? How aggressively should a utility invest in GIC monitoring and mitigation for lines that haven't yet seen a catastrophic storm? How much redundancy should you build into navigation and timing systems that are currently good enough most days? When you underestimate peak risk from a single, rare event, the failure mode is obvious. A big storm hits, things break publicly, and everyone scrambles. When you underestimate cumulative risk because you lack the right long-term metrics, the failure mode is quieter. Things fail a little early, a little more often, in ways that can always be blamed on something else. The uncomfortable truth is that we are making multi-billion-dollar design and policy decisions about space-dependent infrastructure while looking at the sun and the space around Earth through instruments that are in some cases past their prime, and with models that do not yet fully capture the rhythm of recurring, stream-driven stress. We know enough to see the pattern. We do not yet measure it in all the ways that matter most for long-term resilience. At that mismatch, between the precision of the physics in our simulations and the fuzziness of the risk in our planning, feeds directly into the last part of this story, the human part, how our attention works, what we choose to worry about, and why a grey patch on a solar image that quietly sets a clock ticking can be more dangerous, in the long run, than the spectacular explosions that always steal the show. By now you can probably feel the shape of the risk. It isn't a single cinematic blow, it's a slow rhythmic pressure, a metronome in the sun's corona that nudges our satellites, our grids, our navigation, our future missions, over and over, month after month. And yet, if you go looking for space weather in most news feeds, what do you see? You see flares, you see CMEs, you see headlines about massive solar explosion headed toward Earth, illustrated with dramatic animations of a fireball slamming into a glowing blue-white planet. You see, maybe, a map of where auroras might be visible, tonight only. You almost never see a story about a coronal hole that has quietly driven 6 moderate storms in a row, or a graph showing how many extra hours GPS has been degraded this year compared to the last, or a chart of transformer lifetimes shortening over successive solar cycles. That mismatch isn't an accident. It's baked into how our brains and our media ecosystem work. Humans evolved in an environment where the most pressing threats were sudden and local. A predator stepping out from behind a tree, a storm rolling in over the hills, a fire catching in dry grass. The cost of not reacting to something dramatic and immediate could be death. The cost of overreacting, jumping at a shadow, turning back early from a hunt, was usually just wasted effort. We are, to put it bluntly, wired for jump scares. Our attention system is tuned to prioritize rapid changes, loud noises, bright flashes, sudden movements. We are much worse at noticing slow drifts. A river rising a millimetre a day, a bridge corroding over decades, a climate warming by fractions of a degree per decade, an infection gaining resistance bit by bit across a population. We call the dramatic things disasters, the slow ones we usually don't name until much later, when the cumulative harm has become impossible to ignore. Space weather has both modes. CMEs are the dramatic ones, solar explosions that fit neatly into our story templates. A CME is a storm in the way we like to picture storms, a discrete event that we can draw an arrow from Sun to Earth and say, this caused that. Coronal hole streams are the other kind, a background pattern that looks like wallpaper. They're always there in some form. They don't produce jaw-dropping imagery. A dark patch on an ultraviolet image does not ring the same alarm bells as a brilliant expanding halo of plasma. A monthly G2 storm watch does not sound like a plot point. It sounds like noise. Media, for the most part, amplifies that bias. News organizations survive by capturing attention. Attention is captured more easily by stories that have a clear beginning, middle, and end. A visible villain. A single, memorable moment of danger. A solar flare that erupts at 3:14 UTC, launches a CME, and arrives 36 hours later with potential to cause auroras and disruptions is perfect for this. You can put times on a timeline. You can show before and after images. You can count down to impact. You can interview an expert who says, if this happens, here's what might go wrong tonight. A coronal hole that causes slightly elevated KP for 3 days this month, and similar 3-day disturbances for the next 8 months, is not that. There is no single impact moment, no obvious villain image, no crisp narrative arc. It doesn't wipe anything out, just shaves years off hardware life, a few minutes off GPS accuracy here and there, a few extra dollars off airline margins each cycle. Try pitching that as a headline. Recurring solar feature may shorten transformer lifetimes by 5 to 10% over next decade. It's important. It's also, for most audiences, a reflexive scroll past. So we end up with a coverage pattern that roughly says, space weather is flares and big CMEs, and the thing to care about is whether the big one hits. The wallpaper threat, the chronic, moderately bad but highly repetitive stress from coronal hole streams, does not get its share of oxygen. This pattern is not unique to space. It's the same dynamic that plays out with climate change. A single hurricane making landfall with dramatic footage gets wall-to-wall coverage. The long-term upward trend in hot days, or the slow encroachment of sea level, or the gradual deoxygenation of oceans gets more muted attention, even though that's where most of the risk to civilization lies. It's the same with infrastructure decay. A bridge collapse leads the news. The hundreds of bridges slowly dropping from good to fair to poor in annual inspection reports over 20 years do not, until one of them finally fails. It's the same with antibiotic resistance. A new outbreak of a scary pathogen makes headlines. The daily, incremental spread of resistant genes through bacterial populations driven by overuse of antibiotics in medicine and agriculture runs mostly in specialist journals, even though it shapes whether routine surgeries will be safe 10 or 20 years from now. All of these are slow disasters. They don't announce themselves with a single obvious bang. They accumulate. They are, in a real sense, disasters of attention. They take advantage of the fact that our cognitive and media systems are poorly designed to care about long sequences of small, similar events. Coronal hole streams fit the pattern perfectly. They're regular, so they fade into the background. Their individual effects are usually below anyone's personal pain threshold. The interesting part, the cumulative stress, is hard to illustrate visually. They rarely produce a single spectacular failure that can be clearly tied to them in public. The consequences of that underattention are not abstract. When policymakers allocate funding for space weather research and monitoring, they are influenced, consciously or not, by what seems threatening. Big CMEs that might cause continent-scale blackouts are scary. They draw analogies to Carrington 1859 and Quebec 1989. They get hypothetical cost estimates in the hundreds of billions. Budgets respond. Recurring moderate streams that might shave 10% off the lifespan of thousands of satellites, or quietly raise transformer replacement rates, or make precision GPS farming unreliable 3 days a month, rarely get the same treatment. There are fewer glossy reports about the economic cost of chronic G2 storms, even though, if you integrated those costs across sectors and years, they might rival or exceed the cost of a single exceptional event. Similarly, engineering standards and resilience plans often centre on peak loads. How big a current can this transformer survive once? How strong a radiation burst can this satellite tolerate in a day? How accurate does navigation need to be during a rare, severe storm? Less attention is paid to the environment in which those peaks ride. Will you, in practice, be operating your systems much more often in a mildly stressed state than in a truly quiet one? When undercovered risks meet under-designed systems, you get unnecessary fragility. This is where you, watching this, are in a different position than most. You've seen the wallpaper. You know now that a grey patch on an extreme ultraviolet solar image can be more than background texture. You've walked through how that patch becomes an open gate, a high-speed stream, a CIR, a KP jump, a radiation belt enhancement, a slow-motion assault on satellites and grids and timing systems. You understand that the key question is not, will tonight's storm end the world? But how many storms of this size on this schedule can our systems really take? That understanding doesn't magically fix anything. It doesn't shield a single satellite or reinforce a single transformer, but it is a prerequisite for doing those things. New narratives have to be written before new policies and designs can follow. We need to start talking about space weather the way we talk about hurricane seasons, not lightning strikes, as a repeating, predictable stressor that demands routine preparation and long-term adaptation, not as a rare bolt from the blue. We need coverage that says this is the 5th rotation of this coronal hole. Here's what that means for satellite-age profiles and grid fatigue, not just auroras tonight. The existence of a video like this is, in a small way, part of that rewrite. It's an attempt to take something that looks like wallpaper and drag it into focus, to show that the background pattern is itself a story worth telling. Because until we start thinking in those terms, we will keep doing what humans always do with slow disasters, waiting until some specific, undeniable failure forces us to admit that the threat was real all along, and by then, the wound on the sun that set the metronome ticking may have long since rotated away, leaving us arguing over which storm to blame for a decade's worth of accumulated cracks. In the final turn of this story, the question is simple and uncomfortable. How much are we willing to let accumulate before we act differently? And can we shift our attention from the single loud bang to the rhythm we're already living inside before that rhythm brings something important quietly to a stop? At this point, the pieces are all on the table. We have a wound on the sun, a coronal hole that isn't a hole but an open gate in the solar magnetic fence. We have open magnetic highways rooted in that gate, sending a focused, fast stream of solar wind out into the heliosphere. We have a co-rotating interaction region, where that fast wind ploughs into slower wind, sharpening a quiet leak into a moving shock front. We have a magnetosphere that can flip from calm to storming in hours when that front arrives and the magnetic field tilts south. We have radiation belts that don't reset between storms, storing weeks of exposure and quietly preloading every satellite that passes through them. We have an orbital shell that has gone from a few hundred large spacecraft to tens of thousands of machines in a decade, most designed under assumptions rooted in a more episodic view of space weather. We have power grids, aviation networks, navigation systems, and financial infrastructure that have grown to depend on space-based services, as if the near-Earth environment were a fixed, reliable utility rather than a living, changing medium. And we have a sun entering a phase of its 11-year cycle where long-lived, low-latitude coronal holes, recurrence engines, are poised to play a bigger role in shaping our space weather than rare, spectacular CMEs. Put all of that together, and the question that started this story, will it hit Earth, starts to feel almost quaint. The stream is hitting Earth. It has hit us before. It will hit us again, on a rhythm you could write into a calendar. The real question is more uncomfortable. How many hits like this can our systems take before something we actually care about fails in a way we can't ignore? There are, broadly speaking, two ways this can go. In the first, call it the adaptive future, we actually learn from the pattern while we're still inside it. We treat recurring coronal hole streams the way coastal communities treat hurricane seasons, as a predictable long-term feature of the environment, not as one-off acts of God. We fund the next generation of monitoring spacecraft at L1 and L5 before the current eyes go blind. We design new models and metrics that integrate cumulative stress, how often the belts are energized, how many hours per year grids see GICs, how many minor anomalies satellites experience per 1,000 orbits, instead of just counting peak KP days. Satellite builders start treating deep dielectric charging and multi-rotation exposure as first-class design constraints, not edge cases. That might mean more shielding in the right places. It might mean different materials, more aggressive onboard error correction, more redundancy in critical subsystems. It definitely means testing components not just against single, worst-day doses, but against realistic sequences of moderate events spaced weeks apart. Grid operators expand their view of space weather from prepare for the big one to optimize for a world where modest storms are frequent. They invest in better GIC monitoring, smarter transformer designs, and operational procedures tuned for recurrent stress. Regulators and insurers, seeing real numbers about cumulative risk, adjust standards and pricing accordingly. Navigation and timing systems develop serious independent backups that can carry critical loads during days when GNSS is degraded. Airlines bake space weather into their fuel and routing models the way they already bake in jet streams and thunderstorms. In that adaptive future, a coronal hole that keeps coming back every 27 days is still a nuisance. It still costs money. It still produces anomalies and shortens some hardware lifetimes. But the system around it is flexible enough, redundant enough, and well-informed enough that those costs are accepted and amortized. The slow disaster becomes a managed hazard. In the second path, the neglectful future, we keep thinking like we always have, until something breaks loudly enough that we're forced to change. We continue to design satellites as if the main thing to worry about is surviving a handful of big flares and particle storms. We underweight the importance of monthly, moderate charging episodes because they're hard to dramatize and even harder to tie to a single failure in a way that impresses executives and investors. Constellations grow denser. Launch providers stay busy filling the sky with hardware that has, on paper, 7 or 10 years of design life, based on radiation models that don't fully account for a declining phase sun with a strong recurrence engine. Power grids squeeze more capacity out of aging infrastructure, deferring maintenance and a replacement because nothing has obviously failed from space weather recently. Planning documents acknowledge GICs as a theoretical hazard, but treat them as rare, acute events, not as a chronic source of fatigue. We patch over each visible symptom as it appears. Another satellite anomaly here, another unexpected transformer retirement there, another spate of GPS outages during planting season. Each is explained in isolation as bad luck, or component quality, or operational issues. Meanwhile, the metronome keeps ticking. Every 27 days, the same coronal hole, or its successors, sends another stream past Earth. Every 27 days, the belts swell and subside, the electrons burrow a little deeper into insulators, the grids feel another nudge, the ionosphere shimmers a little more than we budgeted for. Well, somewhere along that sequence, a threshold will be crossed. It might be in orbit, a cluster of aging satellites in a GNSS constellation, all launched around the same time, all designed to the same radiation spec, all living in similar orbits, all having endured the same series of recurring storms, finally begin to fail in close succession. Redundancy that once masked individual losses erodes. Timing accuracy slips. Regions of the world find their navigation and time-stamping systems degraded for weeks at a time. It might be on the ground. A key high-latitude transformer, already weakened by years of cumulative thermal and mechanical stress from small GICs, fails during an otherwise unremarkable G2 storm. The failure cascades through a region's grid, tripping other components not because the storm is historically large, yes, but because the system has less headroom than its blueprints assumed. It might be somewhere less obvious. An unexpected rise in insurance claims tied to unexplained satellite anomalies, or a sudden need to accelerate replacement launches because constellations are attriting faster than planned, straining launch capacity and raising costs across the space economy. In that neglectful future, when the line finally snaps in a way that makes headlines, we will be tempted to blame the last event, to point to the specific rotation of the coronal hole that coincided with the blackout or the cluster of satellite losses and say, that storm did it. It will feel satisfying. It will also be wrong, or at least incomplete. because the failure would not be the work of one stream. It would be the sum of dozens or hundreds of moderate pushes that we chose not to count. Between those two futures lies a continuum of choices we are already making. We are not starting this experiment from zero. The coronal hole that triggered this whole discussion has already hit us more than once. It will keep coming back until the sun's magnetic field decides, in its own time, to rearrange. Other holes will take its place. The declining phase of cycle 25 will unfold whether or not we're ready for what it brings. We don't get a vote on the metronome. We only get a vote on how we build and manage the things that have to live under it. Understanding the pattern is a first step. That's what you've been doing by watching this. Taking a series of abstract plots and arcane terms and connecting them into a single, thus coherent story. A story in which the key question is not is a big one coming, but how many medium ones can we take? What we do with that understanding is not settled. We could use it to justify smarter design requirements, more robust monitoring, better public and policy conversations about space weather as a recurring cumulative risk. We could treat coronal holes the way municipalities treat snow seasons, not as surprises but as line items. Or we could file this away as interesting science. Go back to tracking only the photogenic flares and let the metronome tick in the background until something snaps hard enough, in a place important enough, that we are dragged into adaptation by events rather than led there by foresight. I can't tell you which path we'll take. No one can. The wound on the sun will keep rotating regardless. The fast wind will keep pouring out. The CIRs will keep forming. The KP index will keep rising and falling. Satellites will age. Grids will hum. Flights will cross polar skies. Humans will push farther beyond the umbrella of our magnetic field. The open question, one that no forecast can answer in advance, is this. How many times can that metronome tick? How many rotations can these coronal holes quietly lean on the nervous system of our civilization before something critical crosses a line it cannot uncross? And when that day comes, will we recognize the failure as the end of a long rhythmic sequence of small hits we chose not to add up? Or will we point to whichever storm happened to be passing at the time and pretend it came out of nowhere?